Hello, everyone. My name is Kangya Chen, and I'm now in KA Professor Shaoli Jing's group at Peking University in China. In this work, we have studied the prospects for detecting circumbinary exoplanets around double white dwarfs by using two different space-borne millihertz gravitational detectors, LISA and Taiji. For the latter, Taiji, it is a Chinese space-borne GW mission similar to LISA, but has a slightly better sensitivity at low frequencies. So before I outline the method and the results, let me give you a little background about the exoplanets. So far, more than 5,000 exoplanets have been discovered using electromagnetic techniques. But we can see from this figure, most detected ones are restricted to the solar neighborhood by EM detection methods. Gravitational macrolensing can detect exoplanets farther away towards the galactic bulge, but scarcity and unrepeatability can be two of the main restricting factors. A more frustrating fact is that we know very little about planetary systems under extreme conditions. Even though some observational results have confirmed that exoplanets can exist around stars after one or two common envelope phases. Given that more than 97% of stars will become white dwarfs and about 50% of solar type stars are not single, there should be a considerable population of double white dwarfs in our galaxy. Some theories like the planetary migration or the second generation formation process can be used to explain the existence of nearby exoplanets in these systems. So, if exoplanets do exist around double white dwarfs, the detection of such a CBP population would be very promising. However, the fact is that no exoplanets have been discovered around double white dwarfs to date. This can be explained by several factors, such as the intrinsic faintness of double white dwarfs and the sensitivity limits of the current EM methods. Alternatively, gravitational waves can provide a powerful tool for the detection of exoplanets beyond our solar system without the above selection problem. Specifically, we follow the method and the criteria proposed by Tamanini and Danielski in 2019. We also consider a three-body system composed of DWD emitting GWs on the inner orbit with an exoplanet on the outer orbit, and the separation between the planet and the DWD is much greater than the separation between the two white dwarfs. That is to say, this is actually a p-type system. For simplicity, we also consider both these orbits are circular orbits, and based on all these assumptions, this model can be equivalent to a two-body capillary motion. Through the Doppler effect, uh, the observed GW frequency will change, and the perturbation induced by such an exoplanet may thus be extracted from the gravitational wave phase, which is similar to the radial velocity technique. For each DWD, there are 11 parameters characterizing the observed GW waveform, for which we will pay more attention to the amplitude k and the orbital period of the CBP. Then, from the inverse of the Fisher matrix, we can obtain the uncertainties and the correlation of parameters and set 30% to be the detection criterion on both delta k over k and delta p over p. That is to say, a detectable CBP is defined in our work with estimated parameter precision being better than this value. Then we first give some complementary discussions on the detectable abilities with different DWD methods. We know the perturbation k caused by the exoplanet gets smaller with the increase of the total DWD mass. But meanwhile, the SNR will be in contrast higher. So we first fix some other parameters of the DWD and only change the total mass. This figure shows the selection functions of Taiji as an example. The circles denote the detectable minimum planetary masses for each system, and we can see that with the increase of the total DWD mass, the detectable minimum planetary mass is getting smaller, which means that the detection ability is becoming better. Note that the dashed horizontal gray line denotes the deuterium burning limit, which is usually considered to be the upper limit of the exoplanet mass. Therefore, we can define the detectable zone as the circumbinary distance for each system. And we can find that the DZ is also becoming wider with the increase of the total DWD mass. Similarly, we also give a further look at the detecting abilities by changing the mass ratio Q with the fixed total DWD mass. This supports that the detection abilities will not be weakened too much if the Q is close to unity. For more comparisons between LISA and Taiji, we first discuss the possible CBP detections around some known DWDs and select the ones with the higher expected SNRs for LISA and Taiji. From this table, we can see that there are 3 to 4 DWDs whose detectable minimum planetary masses are below the deuterium Berlin limit. We define them as the promising systems. That is to say, if such a CBP population indeed exists around these DWDs, it is possible for us to check it out in the near future and even detect them by LISA and Taiji. Based on the DW population obtained from the mock LISA data challenge, we also present basic assessments of CBP detections in our galaxy during a 4-year mission time for both LISA and Taiji. After choosing the SNR threshold to be 10 in our work, we can obtain such a detectable total DWD population. For the promising systems, we further plot the distributions of IDZ and ODZ. We can see that Taiji is expected to detect CBPs with the planetary orbital size smaller than 5 AU, which is about the distance from the Sun to the Jupiter in our solar system. While for LISA, it is 4.4 AU, a little smaller than Taiji. We further analyzed the detection rates in a more realistic situation by injecting 2 different planet distributions, but considering the time constraints, I have to omit more detailed descriptions and analysis, and all of them can be found in our paper. Finally, we also briefly discussed the prospects for detecting habitable CBPs around DWDs. By definition, the water at the surface of an exoplanet in the habitable zone would be in the liquid phase. After assuming that the HZ boundary estimations for main sequence stars could also apply to DWD systems, we then compare HZ and DZ for each promising system mentioned before in order to say if HZ and DZ can overlap each other. In our work, we have considered different schemes, and the results show that such a possibility indeed exists. To sum up, we follow the previous studies to compare the 4-year detection results between LISA and Taiji in the whole galaxy, which shows that LISA can detect about 6,000 promising systems at most, while Taiji can detect about 50% more events. We also gave some complementary calculations for detection abilities with different values of binary mass and mass ratio. For each promising system, we discussed the constraints on their detectable zones and gave assessments of the detection rates in the whole galaxy. Finally, we showed that it is possible to detect an exoplanet in the habitable zone around these binaries within a simplified model. This work is of general interest for the exoplanet and the gravitational-wave communities. Our results can provide a guide for the following exoplanetary projects and help analyze planetary systems after the common envelope phase in the future. That's all. Thank you.